All right, today I want to talk about the MVP, which is an acronym for the Matrix Vector Product Theorem. Oh man, I have an extra parenthesis. Gosh, all right. Always with the typos, me. And this is abstract at this point. You know, we don't actually have a super great use for this at the moment, but we are going to become maybe uncomfortably familiar with this by the end of linear algebra, because this is really the piece of theory that we need to say, okay, I want to solve this problem. Here are some related matrices, and now I'm going to row reduce and get the answer I want. And you're like, really? You're going to row reduce? Why? And you're like, the MVP. This is the piece that's going to come in handy. All right. So what the MVP says is that if I have an m by n matrix A and I'm multiplying it on the right by an n by 1 vector x, and so I've written x here as the transpose of a row vector. So we've got a column vector x that has n entries in it. Then first of all, the product is well defined. We can actually calculate the product. And even better, the product AX I can write down as a linear combination of the columns of A. And so before I prove this theorem, I want to give you a quick little bit of scratch work to show how we actually use it, because I think that helps you understand like what we're going for in the proof. So here's a little quick example of the MVP in action. We take, let's take the matrix A, B, C, D, E, F. I know, very creative. And let's multiply it by the matrix X, Y, Z. What this is saying is that instead of doing my matrix multiplication algorithm, which if you've heard me talk about matrix multiplication, you don't like walk along this row, dive down this column. So it's actually, if you're multiplying by a column vector, it's simple. You take the first entry of your vector, which for us is X, and you multiply it by the first column of A, which is AD. And then you add that to the second entry of X times the second column of A. And same thing with the third entry in the third column. And so what we're going to get is, if we add this up, we're going to get XA, XD, plus YB, YE, plus ZC, ZF. And that gives us one matrix. It's going to be a 1 by 2 matrix, or sorry, a 2 by 1 matrix. I realize I got those wrong in my head. But it's going to have these entries that look like AX plus BY plus CZ. That's the first entry. And then DX, EY, FZ is our second entry. So that's, it's saying there's like a sort of nice way to calculate this product. Okay, so I want to prove this because we're going to want to use this not so much to actually calculate specific products of matrices, but in fact to like prove things about products of specific matrices. And so in order to start thinking about the proof, I want to think about what are the assumptions that I'm making, what are some relevant definitions that I might need to use in my proof, and what is it that I'm actually trying to show. So the assumptions I want to make, they're right here. The assumptions are that I have an m by n matrix A and n by 1 matrix X, and I might want to remember to like define what their entries are if I want to use lowercase letter entries to make my proof a little bit easier to write out. And I'm going to start by looking at A times X. That's going to be the first thing that I do. I'm going to like actually think about this product. The relevant definitions I'm going to use to get anywhere are the definitions of matrix multiplication, because I'm starting with a product, so I'm going to need to do something with that product. I want to remember the definition of a linear combination, which is essentially a sum of scalar multiples of some matrices, in this case, the columns of A, and the scalars are going to come from the vector X. And I might need to use the definition of matrix equality to say, oh, these matrices are the same because they have the same entries. And my goal is to show this equation, this little equality. And if I have asked you to think about this in groups, then you should pause this video here. Actually, maybe I'll stop recording here and post a follow-up video where we then get into how the proof works. So I'm going to stop for now, and you can find a link to the next relevant video at the end of this one if I figure out how to do that on YouTube. Wish me luck.